Hi everyone, it is our first section. Chapter 2 is called Limits and the Derivative. 2.1 is our limits intro. So you can tell there's some shadows on my page. It's evening when I'm recording this, so I've got my lamp shining down on this. So as you see my hand kind of come across, you'll see some shadows. That's the way it is. Okay, so limits. What's this idea of a limit? So it turns out all of calculus, both branches of calculus, are based on the limit. It's really the limit that helps us go to the next level with all of the concepts in this class. So we're going to spend several sections in chapter 2 just building up what limits are. And then towards the end, we will define the derivative officially. Okay, so where do we begin with the limits intro? I've got an example here. It turns out limits, for starters, are very intuitive. So I've drawn this graph. Take a moment and draw that graph yourself. And while you're doing that, let me just maybe say something. I highly recommend that as you're watching these lecture videos that you are writing all of this down just as if you were in class taking notes. There's a lot to be said about active learning versus passive. So active learning, you're engaged, you're writing it, you're thinking about it. Maybe you're pausing the video and backing up and listening to it again. And you're actively doing things, even physically active, like writing, versus passive learning. So passive learning would just be like, it's not that you're not thinking about it, but you're just listening. And I will tell you, will internalize this information far better if you practice active learning, where you're writing these things down. And maybe if there are questions that come to mind as you're watching, write those down at the moment, and come to office hours maybe and ask me those things. Okay, so let's take a look. We've got this graph. We've got this piecewise function. If you remember piecewise function, so we've got this line here, and I've indicated these points. So this one, this is at negative 1, 2, 3, 4, negative 5, 1. We've got another point at negative 2, 3. We've got this open circle at 1, 3, another point at 1, 4, another open circle at 1, 2, 3, 4, 2. And okay, so what am I asking here? Let's begin with this and ignore what you see there on the right side just for the moment. Let's focus right here. Part A, we're going to think of this. So what I've written here, and I've tried to be a little bit neater. So that's LIM, stands for limit, f of x, and underneath is x arrow negative 2. And the way you would read that, now that's what's on the right side here. When you see that notation, you would say the limit of f of x as x approaches negative 2, and then we'll find out what it equals. So the limit of f of x and the x arrow negative 2 as x approaches negative 2. So now I'm just going to kind of pause for a second and have you think about that. What do you think this equals? What is the limit of f of x as x approaches negative 2 for this graph? Now, if we were in class, this would be a lot more interesting. And typically, there's a few people that are ready to share the answer when I ask this. And well, the answer to this one is 3. And so maybe that doesn't come as a surprise, right? Here's negative 2 on the x. So if you're talking about the function, well, there's the point there at 3, right? Okay, yep, and that would be the answer here. Now there's more going on than just, well, the point is at 3. Notice the way this language, just the way it's worded, right? As x approaches negative 2. And let's just say it equals 3. As x approaches negative 2, it turns out we actually don't care. We're not asking what happens when x reaches negative 2. We're asking what is f of x as x approaches negative 2. So this idea of approaches it's getting at what is it headed towards? It doesn't matter what happens when it actually gets there. And a lot of times you'll see people draw these little arrows, and we would draw one on each side. So as I approach negative 2 from this way, and as I approach negative 2 from this way, well, my function is getting closer to 3. Okay, exactly right. Let's try a different one. Same graph, but now we're looking at the limit of f of x as x approaches 4. Okay. The limit lim f of x, try to make that a little bit clearer here, lim f of x, x arrow 4, as x approaches 4. So we'd say, okay, 1, 2, 3, 4. Here's 4 right here. We'd say, oh, that's a hole. There's a hole that occurs there. So does that mean maybe we don't have an answer because there is no function value at 4? We will have an answer to this. Here's why. Because we don't care what happens when we actually get to 4. We only care what we are approaching. What function value, or you might say what y value, are we approaching as x approaches 4? So we can draw those little arrows again. Okay. As we get closer from this side or closer from this side, what y value are we approaching? Well, the answer is 2. At least the way I've tried to draw it. So what is going on there again? Okay, it doesn't matter that the point isn't there. We're still approaching that 2 as we get closer to 4. Approaches. What is it? What y value as x approaches? Doesn't matter what happens when you actually land on it. Okay, so far so good, I hope. Here's another one. This just barely fits on the screen, it looks like. It's okay. Hey, how about the limit of f of x as x approaches 1? Ooh, now we've got something interesting. Okay, so 1 is right here. Again, apologize for the shadows. As x approaches 1, well, from one direction on the left side, it's headed to 3. But on the right side, over here, it's headed towards 4. Well, does that mean there are 2 answers? No. Both sides, the left and the right, need to be coming to the same location. So if one side is going to 3 and the other side is going to 4, then we don't have an answer. And we write does not exist. Or you often see the abbreviation DNE. There is not an answer to that limit, or you might say the answer is does not exist, DNE. Again, what's going on? For the other 2 examples, both the left and the right sides were going to the same place. But not here. They didn't agree, so we don't have an answer to that. Now you might think, well, is there anything that we can do for something like, when there's this jump, in the function like that? Yes, there is. Okay, so it looks like I've written out exactly what I just said for part C. The limit of the left side must equal the limit of the right side for it to exist. Okay, we get that. I think I communicated that. So it turns out, yes, we can still do something if we think of the limit a little bit differently. So I'm sorry I'm not able to fit all this on the same screen along with that graph, but we can kind of pull the page up and down a little bit. What if, okay, in part D, we're going to say limit, getting a little bit sloppy with my cursive here, the limit of f of x, and now notice I put a little plus sign, a little positive sign there. As x approaches 1 with that little plus sign, that's a superscript. And I know it's written kind of small, but it's x arrow 1 with a superscript plus. That little plus sign means we're looking at the right side only. So think of the little plus as meaning like the positive numbers are on the right side of the number line. So on the right side of 1, what's it approaching? So if we go back to the graph, well, if I'm only concerned about the right side of 1, so I'm on the right, but I'm moving back towards it, well, what are we approaching? And the answer there is 4. So as we approach from the right side only, the answer is 4. We could do the same thing with a little negative sign. The limit of f of x as x approaches 1, and this indicates that you're doing the left side only. Apologize for the shadow. The negative number's on the left side of the number line, right? Okay, so from the left side of 1, let's go back to the graph. On the left side, what are we approaching? Well, 3. So we can still get away with limits if we do maybe this little plus or minus for situations like that. However, if we thought about these, and so just kind of give you some more language, we think of these as one-sided limits, only the right, only the left. We think of these original style as two-sided limits because you're looking at both left and right, and they have to agree. And if they don't agree, well, then it does not exist. Okay. If everything is clicking so far, then we're off to a really, really, really good start. Let's move on. Now, things are always simpler when you have a graph to look at, right? What if you don't? What if you just have the function like the expression, right? So here we've got what f of x actually is. So we're saying the limit, sorry, I'm getting a little bit sloppy with my cursive again, the limit of 5x squared as x approaches 3. Okay. Now let's think for a moment. 5x squared. Is there anything unusual happening around x equals 3? And by unusual, I mean like the unusual sorts of things that were going on back here. So what was kind of unusual? Like if there was a hole, we would call that a hole. If there was a hole in the graph, well, that's something unusual and we might need to be careful about that. Or definitely this situation, we'd call that a jump. If there's a jump, we got to be really, really careful. Okay, when it comes to this function here, 5x squared, does that have any holes or jumps at x equals 3? And well, no, and it doesn't have any holes or jumps at all, right? 5x squared is a parabola, and it's nice and smooth, and you know there's no nothing unusual going on. Well, if there's nothing unusual going on, then we got really lucky, and all we got to do is plug that number right in. So plugging in, and I'm going to just show the steps. We can just plug that 3 in, and that will end up being the same as the limit value. So 5 times 3 squared, well, 5 times 9 is 45. Why am I allowed to just plug it in? Well, go back to the graph. You know, like the non-holes or jumps, you know, like that very first one we did, nothing unusual going on there. There's no hole, right? And there's definitely none of this. So the function value is the answer to the limit, right? This answer happened to be 3. Same idea. The function value is going to be the same as the limit in this case. So we can just plug that number in. And then I've got a note here, kind of the thinking, I put it on paper. Does f of x equals 5x squared have a hole or a jump at x equals 3? If not, we can simply plug 3 in. Okay, fantastic. Well, what do you think we're going to do next? We're getting there anyway. All right. How about this one? The limit. Ooh, we got a good one on our hands now. Our function. This is a rational function. X squared minus x minus 6 all over x minus 3. And it's the limit as x approaches 0. Okay, well, let's ask ourselves the same thing. So for this function, is there a hole or a jump at x equals 0, right? The value that we are approaching. And now if you're thinking to yourself, you know what, as I look at that function, there is something interesting going on at x equals 3, right? At 3, we would be dividing by 0. And so that's unusual. But is there something unusual happening at 0, x equals 0? And, well, the answer is no. At 0, it's perfectly smooth and nothing unusual. At 3, that's a different story, and we're about to go there. But at 0, nothing unusual. Again, we can just plug this in. 0 squared minus 0 minus 6 all over 0 minus 3. And if we simplify that, well, we're just going to get 2. Okay, if we were in class and I had access to the projector, I'd probably graph this function right there, and we could see it and what's happening at 3 and what's happening at 0. So I think what I'll do when I'm done with this, I'll do a quick video of me using an online calculator, and I'll talk about that. It'll be a good time then as well, and we can, what I would have done in class, we won't lose that, but it'll have to be in a video coming later. Okay, let's do one more before we take a break in videos. Part C, and okay, so I hinted that this was coming. Let's do that same function, x squared minus x minus 6 over x minus 3, and now we're going to do the limit as x approaches 3. Oh man. Okay, this will be good. Now here's the thing, we can tell something unusual is going on because we would be dividing by 0 if we tried to plug 3 in. But what exactly is going on? Okay, and at this point, we need to fall back on some of our college algebra skills. Here's what we can investigate. Without even knowing what the graph looks like, let's attempt to plug in the 3. Okay. If we try to plug in 3, we're going to get something surprising. Plugging in x equals 3, not only will the denominator be 0, the numerator is 0 as well. Let's take a look at that. So putting 3 in, we would get 9 minus 3 minus 6. 0 over 0. Okay. And that's really interesting. So it turns out if you get 0 over 0, then there's a hole happening at x equals 3. How do I know that? So it goes back to an idea that would have come up. It came up in the review, and I know you guys are kind of completing that on your own, and you might not necessarily have any questions. But there were some problems where you had to, I think the question was, where are there vertical asymptotes versus holes? I'm actually pulling it up here myself just so I can share with you the numbers I'm talking about. Okay, it's number 17 in the algebra and geometry review. It says determine x values of vertical asymptotes and holes, and then label each of those x values as either it being a vertical asymptote or a hole. So what's going on there? And I'd like to even just point out maybe part B. Part B will be a good one. So part B was P of x. This is number 17 from the review. P of x equals x minus 3 over x squared minus 9. And we're even going to see the 3 happening again. So you might realize, oh, x squared minus 9. We can factor that as x minus 3 times x plus 3. And then we can cancel and get 1 over x plus 3. Okay, so what does that tell us? If you think about this version, the part that canceled out gives a whole. The part that did not cancel gives a vertical asymptote. Okay, so I don't know if that sounds familiar from your algebra, but that's the idea, and that's what's connecting here. So think about it for a second. So what if we were to plug in 3 to this one? And we're really seeing the number 3 a lot, but just go with it, right? So if we plugged in 3, we'd get 0 over 0. And yep, that means it would have been a whole. If you plug in negative 3, you would get negative 6 over 0. 0 over 0. This would have been negative 6 over 0. Still dividing by 0, but not 0 over 0 anymore. So that means the 0 over 0 is a whole. The number over 0 is a vertical asymptote. So here, when we try to plug in 3, we get the 0 over 0. Boom! Immediately we know that's a whole. There's no jump. There's not a vertical asymptote there. Okay, so if there's a whole, there is an answer to this limit question because the left side and the right side are still approaching the same y value. It's just that that y value is missing when you actually get there. Well, how are we going to figure out where that is? What are we going to do? We don't know what the graph looks like. I mean, technically, we're supposed to be able to do this without a graph. All right, here's how we're going to proceed. We're going to simplify this by factoring, and then we're going to try to plug in x equals 3 again. So you may have realized that that numerator factors nicely as x minus 3 times x plus 2. So I'm still going to repeat limit as x approaches 3, get the factored version. Okay, we can cancel here. So this is equal to the limit as x approaches 3. Really getting sloppy with my LIMs. The limit as x approaches 3, but now it's just the x plus 2, and now we can successfully plug in and get an answer. So our answer to this one, 3 plus 2, ends up being 5. What happens, and this is kind of just what's nifty, when you factor and cancel, graphically what's happening is you're filling in that hole. So then you are able to just plug in the 3 and the 5. Well, if you're just filling in the hole, then that is the answer to the limit, because that is what you're approaching from both the left and the right sides. Okay, we need to stop this video here. More to come in the next one.